few short I'll start off with a few short announcements. I want to welcome you all here today to the our user group for Salt Lake City. We are located in the beautiful mountains of Salt Lake City, where it is actually a gorgeous day outside, which is so nice. Um, I'm gonna link here in the chat to our meetup group, which is probably how you all found us, but I'll put it there um, in case someone needs it. So that is where you can find information on who we are, how to stay in touch about when our meetings are. We try to meet about monthly, and I know we talked about maybe having a mix of in-person and virtual meetings, kind of in the spring, but the Delta variant has changed our plans, and we're going to be sticking with virtual meetings, at least for the foreseeable future. We would probably love to see a time in which we would have a mix of in-person meetings here in the Salt Lake area for folks who are local, and then maybe keep these lunchtime for us on Mountain Time virtual talks, because it has been great to be able to build community in other ways. My name is Julia Silgi. I am one of the organizers here of the group. Andrew Red is another one of the organizers, as is, I think I saw Mark here, who's another one of the organizers. So if you have any questions about our group or what we do, please reach out to us. If you are interested in giving a talk about an R package that you use, or a project that you did, or a Shiny app that you made, or something like that, we love to hear from folks in our community. So please reach out about that. This is a friendly and professional space, and we use the R Consortium's Code of Conduct. I just dropped a link to that. And so Andrew and I are in charge of moderation. And so we, just as if we were in person with each other, we would treat each other with professionalism and respect, and we use that. We would treat each other the same way as we are in this virtual space. The next month's meeting is already scheduled. You can see that on our meetup page. I'm pretty excited about it. Emily Robinson is going to be speaking about getting started with machine learning on AWS, the AWS cloud platform for our users. So I think that is going to be super practical and useful. So I encourage you all to come next month. And I think that is it for now, in terms of announcements. I am really excited about today's topic. Greg, who is here with us, is going to be speaking about our packages for using Stan, as you can see here. And so Greg has been using R since it was not R, I guess, has been using was an S user and now an R user. And Greg works at Intermountain Healthcare as a statistician, and also is a teacher at both BYU and the U. And we're so pleased to have you here, Greg. We really appreciate you talking to us about Bayesian analysis and how to use R packages for using Stan. So thank you so much. Oh, I guess we didn't say about questions. I'm sorry. Sorry to interrupt you, Greg. I apologize. So if you want to, while the talk is going on, type any questions you have into the chat. I'll maybe draw Greg's attention to them during the talk, and we can also ask questions at the end as well. And we can use that hand raising feature of Zoom, and can unmute you, or you can unmute yourself to ask questions at the end. So with that, thank you so much, Greg.
Okay, thank you very much. Glad to be here. So a couple years ago, I did a presentation on kind of the basics and intro to Bayesian statistics, but didn't get very much into doing the actual calculations. And so I was thinking with that is that I mainly use this program Stan to do that, but there's the really nice R interfaces, and then there's some other nice packages that work as well. And talking with Julia, she thought that it would be, a good idea that other people might be interested in learning and sharing some of these. So basically the idea is that R recognizes that it may not be the best tool for every job. We can see that in that there are a lot of R packages that are mainly for interfacing with other tools. And so this is specifically the program's called Stan. If you want to learn more about Stan, it's mc-stan.org is their official website, but it's a powerful tool and language for fitting Bayesian models. And so we use that behind the scenes and then use kind of R as the front end interface, do data manipulation, do final plots and all of that in R, but let Stan do the heavy duty computation behind the scenes. So just as a starting example here's some Stan code, and I think most Stan code is actually fairly easy to read. I still have to look up exactly how to write it because I'm not writing it all the time, and I'm trying to remember, okay, do I do this or this? But once it's written down, I think it's pretty straightforward. So this is a simple Stan code for comparing two means, a two-sample mean, though I'm also doing it, I just said two means and two standard deviations. Stan programs tend to have these main steps is a data piece, a parameters piece, and a model piece. And so the data is anything that we will be transferring from R, anything fixed. So I'm going to have n as basically the length of my y vector. And then I'm going to have a y vector that will be a real vector of real numbers. And I'm probably in Stan, arrays and vectors are slightly different, and I'm probably using the wrong terminology. So any pure Stan people out there, I know are cringing, but please forgive me. And then I'm going to have another set of integers that are only going to be either a 1 or a 2, and that's going to be which of the two groups the data is in. And so that's also going to be of length n. So for parameters, I'm going to have an array of length 2 of mu, so the two means, and then also sigma is the two standard deviations, and we'll assume that the data comes from a normal distribution. And so then our model piece here is so I'm just looping through, and for each individual measurement, the y comes from a normal distribution whose mean is based on the group. So we're going to look up the group for that person, and then remember G only has a 1 or a 2, and so it'll be the appropriate mean, and the appropriate standard deviation will be used as the normal. And so that's all we need to run it, but I added a couple other things. So this generated quantities block says, well, while you're doing these computations, let's do a couple other things. And so since we're probably interested in the difference between the two means, we're here just modeling two normal distributions, but so I'm going to calculate the difference as mu1 minus mu2, and I'm going to calculate the ratio of the two sigmas, the standard deviations, sigma sub 1 over sigma sub 2. This part doesn't affect the fit at all, but those get calculated along the way. So we'll look at that. So the RStan package, everything lowercase, is the main tool that I use. There are a few others that do this. There's a command stand or something like that instead of interfacing directly with Stan, uses the command line version of Stan and reads in from the files, and it gets updated a little bit quicker than the others, but I haven't had as much luck using it, and RStan has worked fine for me. So some of the first things that we need to do is, we'll use library to load in RStan, and then a couple options that are suggested every time you load RStan is if we set the options MC cores equals, and then I detect the number of cores, or I can set this in here. There are parts of what Stan does that can take advantage of parallel processing. And so if you tell it how many cores you want to let it use, that can speed things up. This other one, this RStan options auto write equals true, basically tells Stan that it's okay that when we compile a Stan model, to save that and then use it next time. And that's kind of nice in that it does take a couple of minutes to compile the model the first time. But if we've done this, then that means the next time I start R and want to use that same model, if I haven't changed anything, it will use the saved version instead of having to recompile. So that can save a couple minutes each time, which is actually rather nice. So basically what Stan does is from that previous code is when I compile it here, so I use this Stan model, I specify the file where that code was, or is, and Stan basically takes that model and from it writes a C++ program, compiles the C++ program that then actually does the running. So it takes a couple minutes for it to compile, but it runs a lot faster than things written purely in R because it's compiled code, and that runs really fast. And then I save the result of that. Here I just called it 2samp.stan just so I can refer to that model. And if I've got multiple models here, and because it takes a couple of minutes, I discovered a while back this beeper package. It has really one function called beep, and it does that as it beeps. But if you put that after a code that takes a minute, I can go off, check my email, do whatever, and when this gets through, it'll do a little ding sound to let me know that R is ready for me to go back and interact with it again. So I often throw that in for the things I know is going to take a few minutes. Okay. Excuse me. So for the example data I'm going to do, so there's this, in R, there's a package called Palmer Penguins, which is a lot of data on these penguins in the Palmer Islands. I think if I remember right, they're off the coast of Argentina, but somewhere way down south. But I'm going to use that data as an example. So the first question I'm going to ask is there a difference in weight between the female Adelaide penguins on Bisco versus Dream Islands? Sorry about that. And so I figured, it's going to be pretty obvious that there would be difference between the females and the males or between the different species. But, this is one that going into it, I don't know if there is a difference or how big a difference there might be between two different islands of the same species. So arbitrarily, I chose female and that and that. So I load in the penguins data, and then here I'm just going in and saying, okay, just give me these Adelaide female on these two islands, Visco and Dream, and the data is not missing. So W gives me which of those are. So then to pass the data to Stan, I need to create a data object, which is going to be a list. And I need an element in this list for everything in that data statement for my Stan program. So here I have it in the same order. It doesn't have to be in the same order, but it does have to be the same names. And it is case sensitive. So since I used a capital N in Stan, I have to use a capital N here. And so W is just a bunch of trues and falses. So sum is the number that are going to end up in the final data. And then Y is my variable of interest. So that's the body mass in grams. So I give it that subset. And then G is the groups. And so I'm taking the island information as integer, since this is a factor, as integer converts that into the ones and the twos. So I can see here at the very bottom of the slide, you can see the basic structure. So I have 49 penguins that I'm looking at. Here's their first few body masses in grams. And like the first 5 are from Bisco Island, and then the next ones are from Dream and continuing on. So we've got all of that data in there. So that data is ready to run. So if I'm just interested in finding the mode of the data, the peak, this can be used for maximum likelihood if you don't do a full Bayesian analysis. But there's the optimizing function, which runs Stan, but it does the Stan. It doesn't say sample from the posterior, but just find the maximum. So I need to give it my model. So that was the 2samp.stan, and that's already been compiled. And then the bvd.standap is that list with the data in it. So if I run that, it comes back and it tells me the maximum of the posterior, or the maximum likelihood. Since I use default priors, it's almost the same as the maximum likelihood. Is so the mean of the first group, the mean of the second group, the standard deviations, the difference in the means, and the ratios of the standard deviations, the ratio, and I don't know why it gives us this output twice, but those are just the same numbers. But that gives us a quick and dirty way to do that. Now, for simple models, this runs really quick. If you start getting into some of the really complicated Bayesian models, optimizing doesn't always work. There you need to do the sampling. And more often, what we're really interested in is doing the sampling. So here we're going to use the function sampling. And again, I give it here the model, and then the data, and then there are other options. Here I'm just using the default. So by default, it's going to create 4 different chains. It's going to do 2,000 iterations in each chain. And the first 1,000 of those are going to be considered warm-up. And so will be ignored for most of the analyses. So that'll give us a total of 4,000 iterations at the end. And there's a few other options you can set. And I'm saving this in this BVD. So that's, Bisco versus Dream, because those are the 2 islands. Fit1, because this is my first model. Now you can actually, there is a function called Stan that does the compiling and the sampling all together. I like doing it in the 2 pieces because I tend to go back and run sampling multiple times and don't want to have to recompile every time. And so it's kind of nice to just say sampling and give it explicitly those arguments. So if I just say print out the results, now the result is, this is a rather big object, and it's got all 4,000 iterations for all of those parameters. But the print method just gives us this summary information here. So I have for the first mean, so mu is its own array, so it has 2 elements, but the first mean, so this is the mean of all the posterior samples. The standard error is dependent on how many samples we run, so it's usually fairly small and not very meaningful. It's more the standard deviation column that we're interested in. So this is the standard deviation of the posterior for the first mean. And then we have some common quantiles we might be interested in. And then 2 important columns for diagnostics are this NF, so N underscore EFF. So this is the effective sample size. So this looks at the amount of autocorrelation in the data and says, well, because the nature of MCMC sampling, you're going to end up with some autocorrelation. Because of the level of autocorrelation in the data, we have 4,000 draws, 4,000 points we're working with. But for this first mean, it really has about the same amount of information as 3,448. Now, I'm not quite sure how this is approximate, so I think that's how we can end up with an effective sample size that's a little bit bigger than our true sample size, is it's just an approximation. But we want to look at these numbers and just at least make sure that these are fairly big. If these are too small, then we'd want to go back and either find a way to get a more efficient model, or increase our total number of iterations until we get the effective sample size up. And then this R hat number here is it's kind of a measure, since we ran 4 chains. So it starts at 4 different initial points. And then if everything converges nicely, then even though it starts at 4 different points, they'll all come to the same general area. We'll see that when we get to the trace plots. But this is kind of a measure of how different those 4 different chains are. And so if this number is 1 or just slightly above 1, then we're happy. And so these are all 1s. And so that tells us that all of our 4 chains starting at different places all converged on the same posterior shape. And so we're pretty happy there. If those numbers are big, then that tells us that there's probably something wrong with our model or some of the options for how it's fitting. And that gives us a couple other pieces of information down here. But we can look at this. But here, because it fit the mu's and the sigmas, But I'm really interested in mu underscore diff here as the difference in the means. So it looks like the Bisco Island penguins are on average 25.5 grams heavier than the dream ones, if I remember the ordering that I did right. But then I can also see a credible interval here. So the 95% credible interval is that difference could be anywhere between negative 146 to positive 195. And so that tells me that, and considering that, these penguins are weighing over 3,000 grams, so 3 kilograms, a difference of 146 or even, 195 milligrams is probably not of practical importance. So it looks like, at least on those two islands, there's not really a difference, a meaningful difference. But we'll explore more in the posterior here in a minute. Okay. If I want those same numbers that were on the previous slide, I can use the summary function, and it will actually calculate them for all of my draws, but it'll actually calculate them separately for each of the chains. So if that R hat had been different from one, I would have maybe looked at the chains and see which of the chains looked different, or other things. Or I can just do the summary, but the summary, I can save that so I'd have those numbers. Also with summary, there's the parse argument. A lot of the functions in Rstand has the parse argument, where I can say, just give me only certain parameters. So if I didn't want, so if I go back up, it also, this LP and some underscores, that's the log posterior probability. And so that can tell us some things, but most of the time we don't care about that. And so we can say, well, I don't care about that. I just want the summary for just mu diff and sigma ratio, and it would only give me that subset of it. Or I could say, give me just mu, and it would give me both mu's. So parse is used to limit which parameters to give information on. And if you're doing like a hierarchical model, sometimes you'll have a really long vector of different groups. And for your quick summary, you might not want to show that one. So that can be useful there. And then the probs argument is what controls. So here it gave us the quantiles of 2.5, 25, 50%, 75%, 97.5%. But if we would have specified probs, we could have specified which of those values we wanted. So if you wanted an 89% credible interval, you could put in the right values to get that instead. So summary, I already talked a little bit about effective sample size and R hat, but this isn't a slide, so that we'll probably be posting these slides somewhere for anybody who wants them afterwards, so you can go back and refer to those. Okay. Now, if I want to work directly with the samples, I can extract those from that fit object. So I use the extract function, extract it out, and that gives me all 4,000 of those iterations. Now, by default, it doesn't include the burn-in ones. There's an option that I can set to do that. And by default, it just kind of mixes them all together. So it's not, I don't know which chains these are from, and because it kind of permutes them and mixes them together. But these are, a few of the things that I can then look at. So I could do something like, if I'm interested in the ratio of those two means, and I didn't put that in my original model to calculate that, but I can calculate it, on the fly here by saying, okay, from out was the result of extracting out $mu, first column divided by out $mu, second column. Then I'm asking for some quantiles of that. And so this is my 95% quantile or confidence interval, credible interval, and my median for the ratio of the two means. Okay. And in intro stats classes, we usually teach the difference of two means and the ratio of the standard deviations, because that's what works out mathematically nicely. But with the Bayesian statistics, you can actually do any combination that you want. It's pretty straightforward. So in this case, I don't know why the ratio would be interesting, but I just wanted to show that you can do other than the traditional values there. And then here's the histogram of that ratio. So we can see that, 1, no difference would be 1, and that's kind of right in the middle of our histogram. So again, we're saying that, the the ratio of the average of the weights for these penguins is, somewhere between 90% and 110% for the Dream or Bisco versus Dream, whichever way it is. But either way, it doesn't look like living on one of those islands is particularly advantageous versus the other for this case. Okay. Now, one of the big things that this does for us, the Rstand has, is we've got all of those draws from the posterior, and so there's a lot of plots that we can do that give us summary and diagnostic information. Many of these plots is if we just call the plot function and then use the plot fun argument, we'll get the same plots as what I'm going to show here. Or most of these functions are Stan underscore something. So like when I do Stan underscore histogram, is if I said plot my Stan object and then said plot fun equals histogram as whatever comes after the Stan underscore, it'll essentially turn around and call this function. But I wanted to show these. So a quick summary plot comes from just doing the Stan underscore plot on the object. And this is what the results look like. So it shows us the median of each of those variables. And then the default is the red line is the 80% credible interval. And then the black line is the 95% credible interval. And there is one here, it's just so narrow relative to the others. And so here, because these two numbers are so different in scale from the rest of these, here's where it might have been useful to use that parse argument to say, only show me the means or only show me the standard deviations. So the scale isn't making everything narrow here. But we can put in other options. So here I'm saying, okay, just show me mu and sigma. But for the point estimate, show the mean instead of the median. But I actually want to see the whole density estimate. So the whole posterior, not just the interval. And then I want the red part to be the 95% credible interval, and the outer black line will be the 99%. And so that gives me these plots. So now I can see actually these distributions. These are the posterior distributions that we're looking at here. The black line here is the mean, and then this is the whole width is the central 99%, and then the red part is 95% in this case. So you can do a couple different arguments and get a nice summary plot out, which I think tells us a lot more information than just the credible interval. Now, these ones are fairly symmetric and fairly well behaved, so it's not telling us a lot more, but if things were a little bit different, this would be really nice, okay? Another common plot is the trace plot, or sometimes we call these caterpillar plots because you can see they look kind of like a fuzzy caterpillar. And basically that's what we want to see. If everything worked properly, these should be very random, bouncing around with no trends. And it's actually plotting all four chains on top of each other. So we just kind of see chain one as the top one. We can see the others poking around. But if they look like this, we're pretty much happy. And I'll show in a couple of minutes, say, some examples of what we don't want to see. But we can look at that. But again, we can see like here's the mu diff. So again, we can see it's centered around 0. Most of the values are going up and down, up and down around that. And it's just pretty much random. So this is a diagnostic plot. If it looks like the fuzzy caterpillar, we should be happy. Okay. If I use this option, include underscore warmup equals true. So the previous one only showed the last 1,000 iterations of each chain. This one shows all of them. And so it's got kind of this gray background block. So that's the warm-up part. And so you can actually see here, all these mu's, the initial points actually start off around 0, but they all converged up here by around iteration 200. They were in the right neighborhood. But, just to be, I guess, extra paranoid or so, we're throwing away all of these points and only worrying about the last half there. So lots of arguments for each of these functions, so you can go in and look at different things. But in each of these cases, you can see, okay, it starts somewhere, but it fairly quickly gets to the right neighborhood. And Stan_scat does scatter plots. So here you have to specify pars. There's no default in this case. You have to specify exactly 2. So here I did a lot of scatter plots, and most of them were boring. So I don't know that this one's that interesting, but you can see there's a relationship that the bigger the difference is, the bigger mu1 is. That's because, mu diff is a function of mu1 and mu2. So we can see some relationship. But if they're, the normal, the mean, and the standard deviation, and 2 separate means are all pretty independent of each other. So mostly we were just seeing a cloud of points. Here, at least, we see some relationship. But any pair of points we can do with stat. Stan_hist does histograms of each. And I like a little bit better, Stan_dens does the density plots for each of those. And so here's our posterior distributions. And one nice thing we can do with the Stan_dens is if we use pars to say only show me 1, but then I have this separate chains argument, so we can actually see now we've got a density for each chain. And again, this tells us that there's a lot of overlap between all 4 of those. So again, all 4 chains, even though they started in different places, all converge to pretty much a similar posterior. And the best posterior we get is then from combining all of those into 1. But if there was a big difference, that would be something of interest. Stan_AC, that's for autocorrelation. So the function or the methodology that Stan uses is actually better than a lot of other tools for reducing autocorrelation. And you can see here in this data, there's not a lot. Now, for a more complicated model, we'd probably see a little bit more than this. But this, along with that effective sample size, tells us that things mix pretty well. And we've got, a good number of iterations that we can make conclusions based on this data or this run. Okay, so another example is let's look at that same, but let's look at the Gen 2 penguins instead of the Adelaide penguins. So this code is almost identical to what was on a previous slide, just I have Gen 2 now here instead of Adelaide. So I go ahead and I use sampling again. I can use the exact same model because, by passing in n, I could have hard-coded n into the model, but since I passed it in, I can now use the same model without having to recompile. But I'm just using this different data set. And now you see this time we see a bunch of warnings popped out. And we'll actually look at this when we look at our summary information. We have numbers that are all over the place. Some things couldn't be calculated. So this sigma 2 has an infinite standard deviation as our best estimate here. And these numbers are really not very meaningful. So let's look at the trace plot here. And you can see we have a little bit of a problem with mu1 and sigma 1, that even after all the burn in, we still had one chain that took a while to match up with the other. So the other thing I want to show from the output here is you can see the effective sample size. So we have 4,000 iterations, but it's saying that because something went wrong here, our biggest effective sample size here is 36. So we have the equivalent of about 36 iterations, which is not very many. And you can see this, my R hats, 1.08 isn't huge, but it's starting to be concerning. 2.16 is pretty huge for an R hat. I've seen bigger when you get really, really ugly things. But any of these are worth concern. And here, so for my difference in means that I'm probably most interested in, I've got the equivalent of 4 iterations. I don't want to make any definitive statements based on the equivalent of 4 iterations. Okay. So you can see in the trace plots that, here, this chain went wandering up. This one kind of bounced up, and then one goes wandering down. This one kind of stays in the middle, and this red one's just kind of all over the place. Is mu diff, mu2, and sigma 2. I can't even see what's going on there. Something strange is going on. I don't see my nice fuzzy caterpillars. And it seems to be mostly mu2 and therefore mu diff. And my sigma ratio is also doing something weird. Well, why is this? Well, if I, and I really should have done this before, and actually I did do this before I perfectly chose this. The thing is that the Gen 2 penguins are all on Biscoe Island. And I was asking it to fit the mean for Dream Island based on 0 data points. And so that's the reason that, but Stan is so good that you have to do something bizarre like this to get it to not converge nicely. Okay, if you get really, really complicated models, you start getting problems there, and you need to optimize things in that. But if I want to keep the model simple, I had to do something silly like, not give it any data for one of the islands. But I wanted to show an example of things not converging and what you would get with that. Okay, so I could have, either need to go back and give it some data, or the other thing that would have caused it to converge is I did not set a prior, so it used a default prior, which is the flat prior, which isn't very meaningful, and you really should fit priors in that. So if I went back and put a prior on these means, then my posterior would make sense for Dream Island, but it would look just like the prior, but at least it would converge to something. And so that's the other thing you kind of want to double check on. There's been some talk of adding another diagnostic warning, is if your posterior looks too much like your prior, to throw a warning to say, hey, do you really have data here? Do you have meaningful data? Because it might not do that. Okay. I have another example on here you can look through, but I'm going to skip it. It's actually from the Stan manual for another complicated place that has a hard time converging until you reparameterize. But I'm going to skip over that. Okay. So another useful package called Shiny Stan. So what if I have trouble remembering all those plot commands? What if I like clicking my mouse more than typing with the keyboard? Or what if I just want doing some quick exploration? So this is the Shiny Stan package. Is nice. Is it expects you to fit the model using Rstan, but then basically you load Shiny Stan and then you do launch _ Shiny Stan, and then my fitted object here. And I'm doing the first one since it behaved nicer. And basically that will open a Shiny, RStudio Shiny page in your browser. And these are just some screenshots from that. I wasn't brave enough to do a live demo, but you can try it out and do that. So this is where you start off. And there's kind of the diagnose, estimate, and explore are the 3 main pieces. So if I click on diagnose, I get a page like this. And so here's my trace plot. For right now, it's mu1. So if this were live, I could click on here and it would have mu1, mu2, sigma 1, sigma 2, mu diff, and sigma ratio. I can also do transforms if I want to look like at a log or a square root. But here's the trace plot, here's the histogram, and here's the scatter plot with the log posterior. And then there's a few other, the mean acceptance ratio, a couple other plots, but these are the main ones. And there's lots of different things I can click on to get different diagnostics. But here I can click on each of the parameters and see the same output for each one of them, but appropriate. And so good for diagnosing, looking where things might have gone wrong. If I click on the estimate, then this is how I get this plot here. Again, if I type in here, I can limit it to a subset of the parameters. And then for this screenshot, I also clicked on this show options and clicked on to add the kernel density estimates. Otherwise, it would have been just the lines there. But we can see a few different things here. And then if I clicked on this posterior summary statistics, and that's the numbers, it'll even generate a LaTeX table that you could include in your LaTeX report. And explore, it kind of mixes those together, along with here you can do your bivariate and trivariate, and a few other plots as well. But here, so I've got my effective sample size, my R hat, my mean, standard deviation, and credible interval, median there. Also got the autocorrelation. So Shiny Stan does mainly the same plots and same things we saw before, but it's an interactive way. So it's a Shiny page to let you go in and do a lot of that same exploring. So if you don't remember, okay, what was the name of the function to do this plot, or if you remember launch Shiny Stan in this package, it can take you through and show you those as well. Okay. Another nice package is called RstanArm. And basically what RstanArm has is a lot of the common models, rather than writing the entire, writing my own Stan code for something that has been done a whole bunch of times before, is RstanArm takes a lot of those common models, has already compiled the code for me, has it available, and then has an interface function that looks a lot like the regular R model fitting functions, but it's going to use Stan behind the scenes. Okay, so it has the precompiled code for several common models. So as an example here, if I want to look at the body mass G for all the islands, so regular R frequentist statistics, I would do AOV body mass G tilde island data equals penguins. Well, now I put the Stan underscore in front of it. And then I do need to specify some prior information here. And so I'm saying here that I believe that my overall R squared will have a mean of about 0.7, the posterior there. And that was just a rough guess on my part. I wasn't very close, but that gives an idea. But you can see this looks a lot like regular R model fitting functions. What this does then is it finds the right precompiled Stan model, does what it needs with my data for me, sends all of that to Stan. Here I got a couple of warnings. There were 5 divergent transitions. 5 isn't very many, so I'm not going to worry about it. But I could look at some other things. But now if I ask for a summary of this, it gives me something that looks a little bit, it's kind of a cross between traditional R frequentist output and the Stan output. So it gives me information about the model that I fit, gives me for each of my coefficients, the mean, standard deviation, and these quantiles, a couple other diagnostic pieces. Here are the R hats and the effective sample sizes, and a few other things like that. So I've got my quick summary, but then I can still do most all of the things that work on a Stan object will work on this fit1 object. So here I do Stan trace, and so here's my trace plots that I can look and see how well things look pretty good. There again, this kind of random noise, fuzzy caterpillars. The Stan plot, so I can see this here. So here's my intercept and my 2 differences from the intercept. So it looks like the penguins on Bisco are the biggest, and then the others. But here I didn't subset the data, so this is males and females and 3 different species. And there were, I think Bisco Island had all 3 species, and the other 2 only had 2 of the species or other things. So that's part of what's driving this difference here. Okay. Now the Stan AOV and Stan LM are nice and quick, but they only allow a general prior on R squared. So if you want individual priors, StanGLM is the nice one to use there. So here I wanted to make sure that this was a factor, and then I reordered them so that Dream is the first island. That'll be our default one. Just I wanted the comparisons to be a little bit different. But now, so I'm going to say, again, body mass G tilde island, data equals penguins. But I'm specifying a prior here, and I'm using the HS prior, which stands for either hierarchical shrinkage or horseshoe. Both different names for the same prior. So it's kind of a cool prior that you can't really look at it directly. It's a mixture of normals, but it ends up having a really high peak in the middle and then a little bit heavier tails than the normal. So when values are close to 0, it tries to force them to 0. When values are away from 0, it doesn't bias them very much. The Laplace prior also has a peak at 0, but it biases everything towards 0, whereas HS, you get further away from 0, it does less biasing towards 0. So when I look at this model, we can see the effect. So here, remember the intercept, now this is for Dream Island. And now this is saying the difference between Torgerson and Dream. And the bottom of my picture got cut off here, but this peak here is right at 0. And that's the effect of that hierarchical shrinkage, is since that difference was close to 0, my posterior, it has a lot of its mass really close to 0. But comparing to Bisco, that wasn't close to 0, so this posterior looks fairly normal. So that's one thing I like, is it has that horseshoe or hierarchical shrinkage prior built into it. And I can use that for the different things. And you can set a bunch of different priors. If you want to do too much customization in the priors, you should probably write your own Stan code. But there's a lot of flexibility with the RstanArm package. So some of it has more than this, but it'll do a beta regression, conditional logistic regression. Glimmer is generalized linear mixed effects models regression. This JM one's kind of cool, is it's a survival, but it's actually a joint model where you're modeling both a predictor and the Cox proportional hazard type thing, or the proportional odds logistic regression. So you've got a ordered category output, and there are a few others as well, but these are all models that are already built into RstanArm. So you don't have to write your own code, they're already compiled. Things are nice that way. Okay, a quick opinion thing on my side is if you're going to use a pre-compiled model, use the default priors and only look at the intervals in the output, you're not really doing Bayesian statistics. So if you're going to use RstanArm, do customize your priors and look at those different plots. Don't just say, hey, look, this confidence or this credible interval doesn't include 0 and I'm going to call significance. The advantage of Bayesian statistics is doing these extra things, so make sure you do those down. Okay. Another package is kind of like RstanArm is BRMS. It has the interface like the regular R functions, but it focuses more on these hierarchical models. And it has a few others. So here's an example. This is actually a built-in data set on, I think it's a kidney cancer. And this is actually a survival model here. So here we're doing time and then with the censored stuff. So this is, we have some censored data. I'm modeling that relative to age and sex and their interaction, as well as which disease they have. And then I have a random piece here. I'm going to fit a random intercept and a random slope on age for each patient. Then I specify the data, family equals log normal. So this isn't a Cox pH model. This is a parametric survival model. But you can see I can set the different priors. So here for my slopes, so for age, sex, and the interaction, I am setting a normal prior with mean 0, standard deviation 5. I'm setting a half Cauchy prior on the standard deviation. And then I'm setting a LKJ prior on the correlation between, or the within patient correlation measures. And then these are actually the defaults, but they were included there. This doesn't have them pre-compiled like RstanArm, so it still needs to compile and run it based on what you do. But again, it is a kind of a nice R-like interface. And then when we look at the output, we get output that's a little bit more like the traditional R. We can see here's our R hat, and it actually does 2 effective sample sizes. I'm not sure exactly what the differences in those are, but different information for those. And then it has its own plot method, and there are actually like 3 plots here. You only can really see the top one. But so for here for the intercept, here's my distribution and my trace plot. Here's my density for the slope on age. Here's the effect of being female. Again, the trace plot. So we got all this type of information as well. Okay. Another useful package, and I want to make sure I leave a couple minutes for questions, is the Loo package, which does leave one out cross-validation. And both BRMS and RstanArm work with this. The Loo package has details for if you want to write your own Stan code to make so it works with this package. But this is another way to get a measure of model fit and any unusual points. So if I do with the penguins here, now I'm doing a subset to make sure I've got, apparently there were 11 penguins that they couldn't figure out which sex they were, so it's just missing in the data. And that meant I was fitting things on different sides here. So here I'm using StanGLM from RstanArm to fit, a model based just on species. And then I can do the leave one out statistic here. Some code show up there. But it tells me, it gives me this kind of this LU information criterion and a standard error estimate, a couple of different things on it that are useful to look at. You look at it individually, but this is kind of nice for now we compare, because I actually had a few different models. And unfortunately, the way it split out my results. So model 1 was just species. Model 2 was species and sex, but no interaction. And then model 3 was species, sex, and the interaction between those. But then it's kind of nice if I do the LU compare, it goes in and it says, okay, which of my 3 models fits best? So it said fit 3 fit the best. But then here's the comparison. So if you ever use like AIC or BIC, the Bayesian equivalent is called WAIC. And then this LU IC is kind of a even better version. And then the ELPD is this Pareto corrected. I don't remember all that stands for, but it's similar to AIC and BIC for how this works. So this says fit 3 was my best model. So it likes having the iteration or having the interaction. Without the interaction, gives me a difference in the statistic of 6.5, which is moderate but not huge. But you can see leaving sex out makes a huge difference. So fit 1 was my worst model. Fit 3 was my best model. I'm doing this comparison. Fit 2 isn't quite as good a fit as fit 3, but it's still pretty close in that. So the LU model is kind of or LU package is a nice one for doing. It also can give some additional diagnostics. If there's an outlier point, a very leveraged point, it can identify those. And just another way of kind of comparing models. Okay. If you go to CRAN and you look at the RSTAN package, there's like 50 other packages that include or depend or import that package. But most of them were very specific models. But I'd recommend going and kind of looking through the list, see if anything strikes your fancy to be of interest. They're all going to use RSTAN and STAN to fit it. But, there's like some zero inflated models, some other models that might be of interest. Lots of other things do it. But hopefully this gets everybody kind of started using STAN together with R. So we have a few minutes for any additional questions or discussion.
Awesome. Thank you so much, Greg. That was really interesting. I think so if folks, if you've got questions for Greg, you feel free to either use the hand raise function or to type your question into chat and I'll raise it. I'll make sure we get that going here. We just got a couple minutes here and if you have to head off, thank you so much for coming and we'll hope to see you another time. I was gonna maybe kick off questions with asking, do you, one thing as I've, like in my own work and then maybe like working with other people who I'm trying to like get going on things, do you have any thoughts or, advice or things you've run into, especially as teaching, with teaching, with these various packages and installation issues? Stan is something that I've noticed people more than average having trouble with installation, depending on what kind of platform they're working on. I wonder if you have thoughts on that. Like, for example, I've partly because of how the pre-compilation works, right? Like people tend to have an easier time with BRMS than RstanArm or, whatever, things like that. So I'm wondering what your experience has been with that.
Yeah, so one thing I do is you should install our tools if you don't
Which
already.
is for Windows. Our tools is for Windows.
Yeah, for Windows, because you'll need a a C compiler because it's doing that. So if you're on Windows, install R tools. If you're on Linux, you'll already have a C compiler, so that won't be as big of an issue. Most of the time, if you've, part of it, I know I've had people who, because of, they're installing it on a company computer and their IT department has locked down permissions on what they can and can't install, then it can be difficult getting the compiler installed and everything that way. Long ago, I convinced my IT people that, they didn't want to have to install stuff for me. And so it's kind of a don't ask, don't tell. So I can install things.
Yeah.
I try to be careful and only install what I'm supposed to in that. But one nice thing with the Rstand package is if you've got the compiler in place and RTools working nicely, is when you install Rstand, it will install the corresponding version of Stan for you as well.
Yeah.
Do that compiling as well. So as long as you've got the permission to be able to install that type of stuff, just, in our install.packages, Rstand, it takes a few minutes because it's doing a lot of stuff behind the scenes, but it will install Rstand for you. But RstanArm, since it already has everything pre-compiled, is probably going to be the easiest one to use. BRMS and Rstand has to, still compile things.
My experience has been the opposite with people, but I'm not a Windows user. Like helping people who are on Linux it's because it will compile it there for you. You're not trying to install a package that has compiled code in it. Anyway, yeah. Have you tried using? So I personally have not. Have you tried using Command Stanner? Because one of the reasons they made Command Stanner was try to help people with these installation issues. It was like supposed to be like, we know it sucks installing this. Like here, maybe try this issue. This is
I
Command
tried
Stanner. Have you
installing it
tried it?
once
Okay.
because there was a function I wanted that had just barely come out and I wanted to try it.
Yeah.
And it was in the Command StanR, but not in the StanR hadn't been updated yet.
Yeah.
And I ran into a problem and I don't remember what it is
Okay.
now. And
Okay.
before I figured out what the problem was, they came up with a new update of Rstand. So
Okay.
yeah, try Command StanR if you can't do it because it's supposed to have a lot of the things pre-compiled
Yeah.
and work more directly.
Yeah. So Mark Dotson, who teaches, is saying here in chat that he uses Command Stanner as a in class teaching, and that he has better experience with that. Anyway, so those are some thoughts on installation. So it definitely is a challenge, I think, with Stan. And for exactly the reason, though, Greg, that you said at the beginning, that it's something that is an interface to something else. So much like if you're using R as like an interface to Keras, right? Like you kind of end up, banging your head a little bit, right? Like, so the reason why we want to do it is the reason why there's these headache kind of issues to deal with. So there was a question here about from Akash about what contributes the most to like these models taking a long time to converge, like being a long time? Is it like a lot of like having a lot of data, making really complex models? Like what contributes the most to these things just like taking a really long time to converge? And what can you do to make Stan models faster?
Okay. So I mean the big things is probably the complexity of the model, and there was this one that I skipped over, but there's a chapter in the Stan Users Guide 21.7 on reparameterization, which is one of the helpful things, and it's kind of a little took me a little bit of thinking. Is coming from the frequentist least squares perspective, I'm used to fitting an intercept and a difference, in a regression model, because mathematically that works out nice that the test is automatically testing what I want. But if I can do a model like that in Stan, but that means that my intercept and my difference are now going to be correlated, and so the sampler has to figure that out. Now, for a simple model, it can still figure that out fairly simply. But if I fit the two means separately, then they're independent, and that runs a lot faster. And so I have to think, instead of fitting an intercept and a difference, just fit separate, means, and then use the generated quantities to do the difference that I'm interested in. And then there's this idea of the non-centralizing thing, where sometimes if you reparameterize, and there's a whole chapter, and I still haven't fully wrapped my whole mind around it, but they've got lots of examples and good things to try, of different ways to, write your model that makes it easier for the sampler to go around. And this is one of the examples that I just have here. So when I have the model here, so y and x, it's just generating, I don't actually have data, this is just generating observations. But this is actually a 10-dimensional thing, but the standard deviation of x is dependent on y. So when y is a really small number, this is a really narrow standard deviation. When it's a big number, it's not a very good standard deviation, because I get, kind of strange things in the trace plot. But it's basically is that, I've got a big standard deviation here, I've got a narrow standard deviation here. So as it's trying to do updates, if I'm at like this point and it jumps to here, that's a really low probability. But if I'm here and I jump to here, that's a very advantageous one. If I'm in here and I jump either side, it's not a very good, not a new good place to go. But if I jump down here, it's still okay. And so it has a really hard time sampling this model. The R hats, they're not huge, but we can see our effective sample size for Y is 103 out of 4,000. So that wasn't very good. So they just had us, if you reparameterize to where now I have a Y raw and an X raw, which are all independent of each other, but then I transform those to the Y and the X that I'm interested in, then this one ends up sampling much faster and much more stable. Just, by generating, having the main place it's working being more independent and then transforming it into the shape that I want. And so again, that's chapter 21, section 7 of the Stan User's Guide, goes into a lot of detail on that. Anytime it wanders off into a strange space, so if you end up with something that's not identifiable, it's going to work really hard to try and figure out how to do something that it can't do. You want to choose meaningful priors. Again, for a simple model, the initial values, the random ones it chooses are fine. But as a more complicated model, you might pass in initial values that are meaningful to start with, rather than letting Stan just choose some at random. So that'll speed things up. But sometimes it's, you have to look at the complexity. And the other thing is, some of these, most of these models, I didn't want to do any of them live because it does take them a couple of minutes to run. But even if you have, I've had a few models that have been more complicated and a lot of data that take like 30 minutes to run, which these days feels like a really, really long time. But I had a professor point out one time, he says, he thought it was a shame when people spent 2 years collecting their data, and then they pretty much wasted that data by analyzing it the wrong way in order to save half an hour or an hour or 2 days. So why throw away 2 years worth of work when you can do it? Even if it takes 2 days to compile, a complicated one. But I'll often do a smaller number of iterations the first time just to make sure that things look good.
Yeah.
And then I'll go back and do a really long run.
Yeah. Awesome. Yeah, those are some great thoughts. Thanks. All right. So to wrap up, there's been a lot of like good books and stuff and lately out there about like Bayesian analysis or like Bayesian modeling. I wonder if there's any that you have read or liked or would recommend.
Andrew Gelman's Bayesian data analysis with like
Yep.
3 or 4 other authors.
Yep. Yeah, that was
good. The Stan, they've actually split the original Stan User's Guide is now 3 documents because it's so big.
Yeah.
But all 3 of them, so one's more technical, one's more examples. And then also if you go to the Stan website, they also have a lot of user contributed case studies where they basically, somebody said, here's something I learned while doing Stan, here's, description of my data, here's the question I was trying to answer, here's how I stepped through and did this. And, a lot of those case studies are really good. They're actually discussing what they can do to basically turn those case studies into its own little electronic journal.
That's
Because
cool.
those case studies are of that they're quality that they could be journal articles, but you can learn a lot from browsing through some of those case studies.
Yeah.
Um,
Nice.
and that. So I start with the Stan website under documentation. Gelman's book is good. Statistical Rethinking by McElry is another one I really like.
Yeah, I
Um,
really like that one too. And I'm going to put in chat here. Someone has made a version, or they've taken statistical rethinking and taken all the examples and code in it and shown how to do it with BRMS, which is a really nice sort of resource. If you're someone who, codes in R and wants to use Stan and BRMS, you can like walk through the statistical rethinking book and like do it in BRMS, which is really nice. Yeah. All, all right. I know we're past time and we've all got other work and meetings to do. So thank you so much, Greg, for that really interesting talk and for your investment and doing this. Thank you all so much for joining us and for coming. We hope to see you next month for talking about machine learning with AWS, and we'll get going on some other meetings for this fall. So thank you again so much for coming, and we will see you next time.